Hello, hello. We are going to go over quiz number 1 from chapter 9 that was due before spring break when your senior trip. So this was quite a while ago. So number 1, which of these is most likely to form a covalent compound? And again, when we talked about types of bonding, we said you could categorize ionic, nonpolar, and polar covalent based on difference in electronegativity. And we know that covalent is going to be with elements that have very similar electronegativity, which will be found very close together in the periodic table. And so when we look over here, we have a metal and a nonmetal, a metal and a nonmetal, a metal and a nonmetal, and at the bottom, a metal and a nonmetal. There's only one that has two nonmetals. So this is what we would expect to be covalent with their small difference in electronegativity. So they're the ones that are going to be sharing, and that's why it's covalent. Uh, Talking about Vesper theory, again, I gave you 5 Vesper geometries I wanted you to know, even though there was more, but there was only 5: linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. I want you to be able to recognize. So even looking at like number 1 or A or whatever this arsenic pentafluoride, this one would actually have a trigonal bipyramidal geometry, but you don't have to know that. You just need to know which one is tetrahedral. So to do this, it would be helpful to draw a Lewis structure because tetra does mean 4 sides, and many times it might have 4 things bonded to it. But if you have sulfur tetrafluoride and carbon tetrafluoride, which one is it? Now, if you do a Lewis structure for SF4, there are 4 bonds, but there is also a non-bonding pair, which is going to make it what's called a square pyramidal. And that's not what we want. So carbon has 4 things bonded to it and 0 non-bonding pairs. So that is our tetrahedral. Again, if you were to do NH3, hopefully you'd figure out it's trigonal pyramidal, but BF3 is trigonal planar. Again, the difference is this nitrogen has a non-bonding pair where the boron does not. What's the geometry for CS2? So if you were to work out the Lewis structure, you would find that there's a carbon in the middle, and it's double bonded to 1 sulfur on the right, 1 sulfur on the left, with, again, both double bonds. The important thing is it's bonded to 2 separate atoms. So that means it has to be either linear or bent, but it lacks any non-bonding pairs. So it is not bent. It spreads out 180 degrees, and that is linear. pH 3, phosphorus has 3 things attached. So if there's 3 things attached, again, you can already expect it to be trigonal something. But because phosphorus, if you draw a Lewis structure, has a non-bonding pair, it makes a pyramidal shape as opposed to a planar. Next up, we have what's the correlation between water solubility and lattice energy? So again, make sure you know lattice energy is the strength of an ionic compound. So the higher the lattice energy, the more energy needed to break it apart. And so if you're going to dissolve an ionic compound in water, then the ions have to be able to dissociate. But if lattice energy is too high, water can't pull them apart, and it is not soluble. So as lattice energy goes up, solubility goes down. And so we can see that right here. Now, we also talked about melting temperature and hardness, and both of those were directly related. So as lattice energy goes up, solubility goes down, but melting temperature and hardness go up. How many bonds will sulfur form when it has a +1 formal charge? So if you were to draw a structure for this one, so typically we would say sulfur can form 2 bonds because it has 2 non-bonding pairs and 2 unpaired electrons. But the +1 formal charge, we take 1 electron away from a non-bonding pair, and so then it has 3 separate non-bonding electrons. And so it is able to make 3 bonds. Again, the quick way to know this is, again, we would normally say sulfur can make 2, but that +1 gives it 1 extra bond. In contrast, if it was -1, where it would gain an electron, it would only be making one if that was the case, but it's not. Which of these is most likely to be an ionic compound? So again, ionic will have a large difference in electronegativity. And so we know there's a larger difference if they're on opposite sides of the periodic table. So we're pretty much looking for which one has a metal with a nonmetal. So the first one has two nonmetals, and the last three have only nonmetals. So there's really only one option, iron chloride, where you have a metal which has a lower electronegativity, and chlorine which has a higher electronegativity. So that has that greatest difference. A molecule has 3 single bonds and 1 lone pair. What is it predicted to be? So again, as opposed to just giving a chemical formula, this just goes and says 3 things are bonded, 1 lone pair. So with 3 single bonds, and again, it wouldn't really matter if it was single or double. All that matters is with 3 things bonded, it's going to be one of the trigonals, which this one doesn't even have trigonal planar as an option. But with 1 non-bonding pair, instead of trigonal planar, it's trigonal pyramidal. Trigonal bipyramidal is what you would get if there were, let's see, 5. It needs to have 5 different things bonded to it, but that's not one we covered. Hey, this one's pretty simple. Which substance is held together by shared electrons? Again, those are covalent bonds. That is molecular. Which one would have the highest lattice energy? So again, what we're looking for is lattice energy goes up as the charge increases from plus or minus 1 to 2 to 3, but also as the size gets smaller. So if you look at all of these charges, they're exactly the same. +1 and -1. If you were to look at them up, they're all from the alkali metals and the halogens. So if the charges are the same, then the factor we need to look for is size. So the smaller the atom size, the closer they get together, the stronger, the higher the lattice energy. So we need to know which one is going to have the smallest. And on the periodic table, we know as you go up towards the top, they get smaller. And so of these, we have lithium is higher up than potassium and sodium, and fluorine is higher up than iodine. So lithium fluoride has the 2 smallest ions and would have the highest lattice energy. We would like to know what's the molecular shape of CHF3. So again, you could draw a Lewis structure, but what you'll find is carbon has 4 things bonded to it and 0 lone pairs, and that's tetrahedral. Metals are ductile because metallic bonds are nonspecific. That's true. Again, ionic compounds, they're brittle. Molecules, when they're solid, they're brittle. But metals, they're ductile and malleable because they don't have specific bonds. Again, all they have is their electrons shifting and sliding around. So you can press on a metal, and because of that electron C theory, the idea that electrons are just jumping and moving about easily, it allows them to be deformed without breaking apart as long as the metal atoms are fairly close together. CO2, there's 2 things bonded to carbon. There are 0 lone pairs, making it linear. Again, if it had any non-bonding electrons, it would be bent. Which has the lowest lattice energy? So earlier we had one for highest, and all the charges were exactly the same. But this time we have +1, -1, +1, -1, +2, -1, and we don't care about the subscript, +2, -1, and I hope you didn't pick SCl3, sulfur hexachloride, because that is a molecule, and lattice energy deals with ionic compounds. So if we want the lower lattice energy, we want smaller charges. So instead of +2, these are both +2. Those are going to be higher. It's going to be potassium or sodium. But then to go even lower between the two, we want a larger atom. So potassium ions are larger than sodium. We know that because it's further down on the periodic table. And so since the bond length is further, it makes the lattice energy lower. Now, covalent bonds, pretty much there's similar trends to lattice energy. Instead of talking about the charge, if we want to know bond length, we look at, is it single, double, or triple? And longer bond lengths will have single bonds. As you go to double and triple, they get shorter. Then the other factor, again, similar to up here, is the atomic size. So bigger atoms lead to larger covalent bond length. So between Cn and Cp, since phosphorus is the bigger atom, it will lead to a bigger bond length. Which one of these can have an expanded octet? So the next quiz will have some more discussion of hybridization in valence and molecular orbital theory. But early on, I wanted you to know you could only have this exception to the octet rule when d orbitals were found, and you only get d orbitals when you get to the third shell. So carbon in the second period does not have any, there are no 2d orbitals. Same thing with oxygen and nitrogen. Now, sodium is in the third shell, but it's not going to be making covalent bonds, so we're not expecting to have expanded octets. But sulfur, if you look up the structure of sulfate or sulfite, it's sulfur with 12. Sulfate has, let's see, 2, 4, 6, 12 electrons associated to it. And so that would be an expanded octet. If you're drawing multiple Lewis structures and we're dealing with those formal charges, we talked about a set of guidelines that handle it if it's neutral or charged. And so this is basically pretty much exact what are the preferences. And it was pretty much the smaller they could be or the lack thereof is better. We did talk about if they're negative, if there's a negative charge, it goes on the most electronegative atom, but this says positive. And this one says larger is better. And again, that's the opposite. So look over those guidelines and you do that. Here's nitrate. And it says, hey, it's violating the octet rule when we have these formal charges. Because typically oxygen has 2 bonds, nitrogen typically only has 3, and we see that, there's one less or there's one more. Now, you could just easily just count the number of electrons, 2, 4, 6, 8. Each bond counts as 2 electrons for both atoms, and what you'd find, 2, 4, 6, 8, is no. There is no violation. The octet rule is conserved even when there are formal charges. We did one that already looked just like this. NH3, it's trigonal pyramidal. With 3 things bonded and 1 non-bonding pair, it's pyramidal, not planar. And which one of these is incorrect? So A looks good. Nitrogen has 3 bonds and 1 non-bonding pair. Methane looks good. There's 4 bonds to carbon, no lone pairs. This is hydronium, and typically oxygen would have only 2 bonds, but 1 non-bonding pair. But because of this positive, it loses an electron and it's able to make a 3rd bond. But the one that's wrong is here. Now, if you count up the electrons, 2, 4, 6, 8, everything has an octet, but what it's not showing correctly is the formal charge. For it to be correct, if nitrogen typically has 3 bonds and 1 non-bonding pair, but here it only has 2 bonds and 2 non-bonding pairs, each of these nitrogens should have a -1 charge, formal charge next to it. But it doesn't. And then, yeah, fluorine looks great. So that is quiz number 1. So hope this was helpful. Again, you can always email any questions you have. If you want to Zoom, send me like a request and I'm probably around to do it. Or then I could probably say, hey, within an hour time span, we could make that happen. But yeah, I will send out the quiz tomorrow, or the test tomorrow morning, and you have 2 hours to complete it starting from when you open it. But I will leave it available it just needs to be turned in before noon tomorrow. because then we're starting the next chapter. Have a fantastic day.